Hello, I welcome you all to this another screencast. The problem reads uh, determine the normal force, shear force, and moment in the beam at sections passing through points D and E. Point E is just to the right of 3 kip load, and draw the shear force and bending moment diagram. These are the part I've just included. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So first things first, let's draw the free body diagram, but we need to separate this particular continuous beam. It's a continuous beam, roller supported at A and fixed at C, and then there's a hinge pin supported B. So separate it at B, and that's when we can apply the available equations of equilibrium effectively. Okay. So we've done the separation, which I've drawn here in advance, and then we just apply the equations of equilibrium quickly, and then start finding the support reactions. All right. All right. We have found all the support reactions. We have found all the support reactions. So let's move on to the next step, which is doing a section at D. We need to do a section at D so that we find the internal forces at D and C. So let's start with D. We have the left hand side, we have the right hand side. Of course, we're going to use the left hand side. We always go with whichever we perceive as our simplest. For me, my simplest is the left hand side. So let's draw that. Let's draw that quickly. So we'll have something like that, and then we'll have loading. Let's say our loading is something like this. Okay, so there we go. At A we have 3, and then this point is A, this point is D. Okay, we are going to have VD, we'll have MD, and then we'll have ND. Then this point here is our Q. Let's write it in red. This is our Q, defining the maximum intensity. So we need to write this load in terms of Q. We can write this in terms of the linear function, that is mx by mx plus c. Remember this, y is equal to mx plus c is a linear function. The load is varying linearly. M is the gradient, which is a change in y, divided by a change in x, which is just 1.5. Okay, change in y, 1.5, divided by the change in x, which is 12x. Okay, c is equal to 0. We know that c is equal to 0. We are starting from 0. Okay, this is equal to 0. So this, if we were to divide it, it gives us a 0.125x. Okay, 1.5 divided by 12. All right, so that is the function of x, which is our q here. All right, 0.125x, and therefore finding this value here, we just need to multiply the area under the load diagram, which is just half. This is half times the length of this part here is 6, of course. So it's half times 6 times Q. And what is our Q? Our Q is 0.125 by X. And what is our X? Our X is our 6. And then this gives us a 2.25, right? Okay, so 0.5 by 6 by 0.125 by 6. Alright, 2.25. And the location of this load is at 1/3 of 6, which is just equal to 2. Okay, it's just equal to 2. Alright, so with that information, we can apply the equations of equilibrium. We'll say summation of moments about point D equal to 0, and clockwise being our reference. So we have a minus 3 by 6, a plus 2.25 by 2, okay, and then plus MD equal to 0. Therefore, our MD is just going to be equal to, so it's minus 3 by 6 and plus 2.25 by 2. So this gives us a positive 13.5 cubic feet. Okay, that's our MD. And then let's find the other component, summation of forces in the Y equal to 0. Okay, what do we have? We have a minus 3. We have a plus 3 minus 2.25 and then minus VD equal to 0. And therefore our VD is just going to be equal to as 3 minus 2.25. So this gives us a 0.75 cube. Okay, and then let's find the other one, which is summation of forces in the X. Okay, so we have summation of forces in the X equal to 0. Okay, we know that this one, just our ND is just equal to 0. Alright, so let's do another section quickly. We've been told we do another section to the right of 3 cubes, so we'll do a section there. Initially we are done there, so we are doing here to the right of E. And then we have the left hand side section and the right hand side section. We're going to use the left hand side. For me, that's the one I'm going to pick. So if I was to draw this quickly here, I will have something like this. So this point here is my A, this B rather, this is my B, and then this point here is my E. Since I'm using the left hand section, this loading will be included, which is 3 cubes. Then here I have another internal force at this support, at this joint, a pin joint. The length of this is a 4 feet, and here we expect to have VE, ME, and NE. Right, so let's apply the summation of moments. So summation of moments about point E equal to 0 and clockwise being our reference. Okay, what do we have? We have 6. I think this can fit here. We have 6 by 4 plus ME equal to 0, and therefore our ME is just going to be equal to a minus 24, right? Okay, so let's bring it down. It can't fit. Maybe let's push this a little bit up so that we just have a little bit of space. Alright, we push these things up like so. Alright, so there we go. Therefore our ME is just going to be equal to minus 24 cube feet. Alright. That's 6. That was 6 by 4. Okay. And then we have summation of forces in the Y equal to 0. Going up in our reference, we have a minus 6, a minus 3, a minus VE equal to 0. Therefore, our VE is just going to be equal to minus 9 cube. Okay. And then we have a summation of forces in the X equal to 0. Okay. So we only have here NE is just going to be equal to 0 cube. So we have MD. We have MD equal to 13.5. Then we have VD equal to 0.75. We have M, and then we have the normal force ND equal to 0 cube. Right, this is 0. Great. Then we have ME equal to minus 24. Right, minus 24. And then we have VA equal to minus 9, minus 9, minus, and then we have the normal force, of course, equal to the normal force, which is just equal to 0. Great. So we have all this. So what we just need to do now is to start drawing. So for us to draw, let me just move these units. Okay. So I have a little bit of space. So we are going to use the differential equation V prime is equal to the lateral distributed force, and V itself is just the area under this lateral distributed force, and M prime is equal to V, and M itself is just equal to the area under the shear diagram. So quickly we start drawing at A for our shear diagram. We have our initial value of 3. Okay, we have our initial value of 3. Let's put a 3 there. And then we have this distributed force. So shear at B is just going to be equal to 3 minus the area, this area under this triangular distributed force, which is negative and increasing. Okay, so the slope of our shear diagram will also be negative and increasing. So this minus the area there is just 1.5 by 6 by 12. So this just gives us a minus 3 minus 1.5 by 12 half. Sorry, there's also a half there. It's 1.5 by half by 1.5 by 12. So our VB is just going to be equal to 3 minus 1.5 by 12 by 0.5. So this gives us a minus 6. Right. So from here we are going to move, like we said, shear, the loading is negative and increasing. Therefore, the slope of our shear will also be negative and increasing. So negative and increasing will have a slope like this. Okay, so let's say that is our value of 6 there. So let's say this is your value of 6 here. This is 6 kips. Okay, and then since the pin can transfer shear, it transfers translational forces. The pin can transfer horizontal forces and vertical forces, and the shear is a vertical force. So it can transfer that. So we expect this from B to E. Since we don't have any lateral distributed force from B to E, we are just going to have uh, a zero slope for our shear diagram. Okay, so it will just be a straight line like this. All right, then the moment we reach E, then negative 6 will add up with the negative 3, so this will move downwards. This I'm doing it a little bit fast. Move downwards like so. Okay, so this will add up. So shear at VE is just equal to minus 6 minus 3, which is just equal to minus 9. So this value here is minus 9. And then from E to C, again, we don't have any lateral distributed force, therefore the slope of our shear diagram will be 0. The slope of our shear diagram will be 0, which is just a straight line. And then when we arrive here, we found that the value at C here, which I just forgot to include here, this value from this support, remember, CY, we found it to be equal to 9, remember, okay, 9 kips, this is a 9. So this is the one that is going to close up. So our shear at our VC is just going to be equal to minus 9 plus 9, which is just equal to 0. So it's the one that is just closing up our diagram like so. Okay, so there we are done with our shear diagram. This is plus, this is minus. Like we said, a pin at B transfers forces, translational forces, but a pin does not transfer a moment. Okay, so we expect moment at B, which is a pin, to be equal to 0, right? Okay, right. So now let's draw the shear force, the bending moment diagram. Let's draw the bending moment diagram. At A, we don't have any initial value for moment. We have a pin. We don't have any cap applied there. And because we don't have any moment, initial value of moment, we expect moment at A to be equal to 0. All right. So now let's look at, we know that moment is the area under a shear diagram, and our shear is a polynomial of degree 2. Therefore, our moment will be a polynomial of degree 3. So then we'll need to find the equation that governs our shear so that we are able to find the moment at B. Okay, but we know that moment at B is going to be equal to 0, and it's a polynomial of degree 3. So you can do a section, the normal section, the way we've been doing it. You cut this beam from A to, we are just considering this region A to B. You can do this, okay, where you cut a beam, like this point is A, this is our X, if you remember this. Then you will have a V there, you will have moment, okay, and normal force. You can do this and work out, you'll have your equivalent force there, you'll have your Q there, okay. You can do this if you want to, then you can find the equations, or you can also just use the integral, the differential equations directly. So what I'm going to do, I'm going to use the differential equations directly, and we'll find moment at B, which we expect to be equal to 0. All right. But before we do that, we need to find the function that governs the shear, right? So that we integrate it from 0 to 12, and we are going to find moment there equal to 0. So our shear, okay, this is in the region AB, okay. Our shear function, okay, which is a function of x. We are just going to put it like x, and x it varies from 0 to 12. Okay, so this is going to be equal to the initial value of our shear diagram is 3. Then we need to subtract this other value of the area under the loading diagram, okay, to come up with this quadratic shape of our shear. So we'll have integral of q dx, right? Remember this? And we said our q is just equal to 0.125x, okay? So plug it in there. Therefore, we have v of x is equal to 3 minus integral of just 0.125x dx. And therefore, this gives us, if we are to integrate this as an indefinite integral, this gives us 0.125 x squared divided by 2. Okay, so this is the function that governs our shear. Okay, and it's the same function we are going to use for finding this point here where our shear is equal to 0. We'll need to find this point later on for us to find the maximum value, right? Here shear is equal to 0. So we need to find this later on. Okay, we need to find this. We need this length, so that we come and find this point where we have maximum moment. So with this function, we can therefore now find our moment at B, which is going to be equal to 0 mb. So our mb we expect it to be equal to 0 using this equation, okay, because we know that at B, which is a pin, moment is equal to 0. So integral from 0 to 12, 3 minus 0.125 x squared divided by 2 dx. And if we integrated that, we'll have a 3x minus 0.125 x squared cubed divided by 6, integrating from 0 to 12. And therefore, this gives us, if we did the integration, let's do that. If we integrated, if we evaluated this, let's do that, we should get a 0. So 3 by 12 minus 0.125 by 12 cubed divided by 6. For sure, we are getting exactly what? A 12. So let's plot that quickly. Like we said, this is a quadratic. And when we look at our shear diagram from, let's call this point here where we have the maximum, we call it point F. Okay. So we are saying okay, this point is A, okay, and then this point here is B. So we are saying from A to F, the shear is positive and it is decreasing. So expect the slope of our moment diagram to also be positive but decreasing. So you will expect something like this. Okay, we'll find that point later on. And then from F to B, the slope is negative and is increasing. Therefore, expect this to just go like this. Right, not good, not too good. So you just expect a curve like this. Okay, you expect something like that. So we need to find this point here where you have 0 slope. That's the maximum point. All right, so like we said, this one is a positive moment. We'll find this value. Let's find this value here, the maximum point. And for us to find this, we just need to, let me wrap this. For us to find we said our shear, we had calculated our shear diagram. The equation is just 3 minus 0.125 x squared divided by 2, right? So for us to find this x here, we said shear at that point is equal to 0. Okay, so we need to find that value of x. So we just equate this to 0. Okay, and once we do that, we just have a 3 is equal to 0.125 x squared divided by 2, and therefore our x is plus or minus, we have a 6 divided by 0.125, root of that, it gives us a 6.93. so this value here is we are getting a positive, is a 6.93. So now plugging it in our moment diagram, in our moment, therefore moment at f, which is maximum, we'll say moment at f. Moment at f is a maximum value. Okay, it's just equal to the integral from 0 to 6.93 of 3 minus 0.125 x squared divided by 2 dx, and therefore our mx, and therefore this is equal to, this is just going to be equal to integral of 3x minus 0.125 x cubed divided by 6, evaluating from 0 to 6.93. Then you find this value. What is the value? Just plug in that value there. So you have 3 times 6.93 minus 0.125 times 6.93 cubed divided by 6. So we have a 13.86. So this value here is just 13.86. Alright, let me just check it. 3 pi 6.93 minus 0.125 by 6.93 cubed divided by 6. 13.86. Great. So that's the value. Basically, that's about it. We found that value there with these equations. If you are not comfortable with using these integrals, these differential equations, you can just do the sectioning method. Okay, but it's important to have knowledge of both so that you can choose whichever is simpler for you. So let's draw the shear, the moment diagram. Let's draw the moment diagram from B to E. From B to E, the slope from B to E, the slope is shear there is negative and constant. So you expect m prime, slope of our moment, to also be negative and constant, and this magnitude is just equal to the area under a shear diagram, so it's minus 6 by 4, which is equal to just minus 24. So let's draw that. So from there to B to E, we just have a straight line like this. So let's imagine that is our value of 24 there. This is 24 minus, and then from E to C, V is again negative and constant, and M prime is also going to be negative and constant, and therefore magnitude of our moment is just going to be equal to minus 9 by 4, which is just equal to minus 36. Okay, so moment finally at C is equal to algebraic sum of minus 24 minus 36, which is just minus 60 rather. So the slope is negative and constant, so just expect a line like that. This is something like that, and that value there we said is minus 60, which we just put like that. And finally we have a closure. We have a 60. You've seen we have a 60 at C, which is clockwise. But the internal moment at C there, if we were to do a section just here, if we were to do a section there, you will find that we'll have a clockwise, a counter. If we are to do a section, we'll have a counterclockwise like this. Okay, so if we are to do a section here, we'll have a counterclockwise like this, which is a 60, and this is the one that does the closure. All right, when we sum them up together, it gives us a 0. Minus plus a plus gives us a 0, like so. Okay, so this is negative. So already, I guess we are done. I guess we are done with this particular problem, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.